within this lecture. Okay, so we talked about the CUDA architecture, evolution of CUDA, and what we need to do. So I'll give you guys a refresh on this. The main functionality of CUDA is that whenever we want to run something on a large scale, we want to parallelize something. What we do is we have two things. We have the host code, what we call the application where we are running on, and we have the device code. So we run that in the GPU itself. So it's pretty much basically CUDA CUDA to be running on. You need special hardware, especially we need NVIDIA GPUs in order to do this. Otherwise, we won't be able to get up and running. There are like open source versions or alternatives for this. We call that open CLI, but it is not that much popular given the support, given the hardware limitations and all. NVIDIA and CUDA tend to be the market lead. So we can assume that the CUDA is like a general purpose or general thing that you will find on when we are working on when we are working with parallel computing and all. Okay. So we just had a look on the GPU structure. We just have these components. We have the CPU and we have GPU, and the communication between the CPU and the GPU happens between this using this PCI bus. So during the execution of CUDA code, memory exchange happened between the host and the device. That means whenever we want to execute something, the host need to prepare everything. The host need to prepare the data set and everything. And once it is done, the code will be executed on the device itself. And once the device, once the GPU has or the device has been executing the result and everything, they copy back these things to the CPU or the host code. So whenever we want to work with one of these GPUs and CPUs, make sure this PCI bus is doing the communication. Okay, so we will look into a sample of CUDA code. Then you guys will understand how this works, how the flow is working, and everything. So we have special functions, or we can say keywords that help us to do so, and make sure the code that we are going to be running on is going to be based on C or C++. But CUDA has the CU extension to indicate okay, this is a CUDA code rather than a C or C++ code. And remember, CUDA supports both C and Python, but most of the time the developers find C version more robust. But Python version also have the more user interaction, because Python seems to be the language of choice when it is coming to AI and Bitcoin and stuff, cryptocurrency and stuff. So when we are working with most of the time, you will find CUDA code written in C or C++ syntax, but they're interoperable with Python as well. So don't worry about that. And one thing that we need to do is we need to understand how the GPU has structured this way, how GPU is going with the implementation of the GPU and how it achieved this parallelism. So first thing that we need to know some terminologies. We talk about the host, we talk about device, SM, and computing compatibility. And we need to know few important methods or important functions we call the kernel function, the device function, and there are limitations. Okay, so we'll look into the kernel function and device function when we are exploring a sample code of CUDA. But there are certain limitation on each of these function with the keyword they are using, what they are supposed to do. So first thing first, we need to understand some of the first thing we need to understand that the concept of CUDA threads. Okay, so we talked about software related threads when we are dealing with Java and everything, but in CUDA we have the same terminologies, but in a different context. So don't get confused with the threads that you have found in Java and all. These threads are like a little bit different, but they are conceptually they are representing the smallest lightweight execution points. So in CUDA, threads are extremely lightweight compared to CPU threads. So you guys can remember in CPUs we have threads. Okay, so we are talking in here in terms of threads. Okay, so in CUDA, you can treat a thread as the smallest execution point. Okay, so when we give something to execute, when we give something to process, a thread is the most fundamental execution point in a GPU. So you can consider a thread as a worker who is doing what it's supposed to do. But in contrast to CPU threads, the main difference is that in CUDA threads there is no context switching. Okay, no context switching in the sense. So if you guys can remember, in a CPU, if you want to execute something, if you want to execute a certain program, what a thread does is what the CPU does is when they are allocating resources, say for instance, there are multiple programming in execution for a CPU, and once execution started for the multiple application, a thread can come available because let's say for instance there is IO dependency or network dependency. While that is happening, the thread become idle. That means there is no work to be done until something is completed in a CPU. So while it is idle, what the CPU does is, since it is idle, it will reallocate that resource, that thread, to another process. Okay, that means there are no waiting times. If something got stuck, if something got waiting, immediately the CPU will reschedule or reassign some task for that thread. So thread is always busy in CPU level. So what we do, what we tell when we are assigning another task for the CPU, or when we assign another task for the thread, we call that as context switching. Okay, so while we are doing context switching, what happens is really we assign another task for that thread. Okay, so the thread is always busy, thread is always executing something. When they are assigned with a new one, assigned with a new task, when they are executing, we call that task context switching. Okay, so but in GPUs, a thread it is not doing any context switching at all. Once they started execution, resources are allocated to each thread until it completes its execution. Okay, so there is no context switching. In a thread, if you assign a task for the GPU, until the full execution is done, this GPU is not assigning another task for that thread. So the thread is always what we call is always allocated to execution, no context switching. Okay. So next thing that we need to know, a thread and a warp. Okay. So warp is what we call a group of consecutive threads which are executed single instruction, multiple data, consistently on a single SM. Okay. So when we group 32 threads, okay, when we group 32 threads, and they execute a single instruction on multiple data concurrently on a single SM. So we can assume that we can tell that a warp is a group of 32 threads. Okay, so their instruction execution is single instruction on multiple data. If you guys can remember, we have this architecture at the beginning. So they, in a warp, what they do is they execute a single instruction on multiple data. So warp can be something similar to a mini processor or mini CPU, if you like to call it that way. But in a nutshell, warp consists of 32 threads. So these threads are executing a single instruction on multiple data, and concurrently on a single SM. SM is for stream. If you guys can remember, streaming multiprocessor, SM. So we are executing. We are grouping our threads into 32 blocks. So when we do that, we have a warp. Okay, and it is called it is also called a single instruction, multiple threads. Okay, we can also call it that. So SIMT, that's what we call a warp. Okay. So next thing is we need to understand is what we call a block. Okay. So group of 1 or 2 or 3 dimensional threads divided into warps. Thread ID is from 1 to 13 assigned to the first warp. Thread ID is 32 to 63 assigned to warp 2, and so on, so executed by a single SM. So a group of 1-dimensional or 2-dimensional, 3-dimensional data, we call those as a block. Okay, so the block number, it is divided thread from 0 to 31. So including 0, we have up to 32. So we call that as a block. So the IDs are given for these threads based on the block and the thread ID they are corresponding. Okay, so we'll look into a block when we look more in here, and the final wrap around is that a grid. Okay, so we have a grid. So a group of 1 or 2 or 3-dimensional blocks can be executed in the all devices stream multiprocessor. So it is like what you call the Russian dolls. So we have a thread consists of 32 thread. We have a warp. When we conclude 1-dimensional, 2-dimensional, 2-dimensional threads, we have a block, and it's when we have a number of blocks, we have a grid. Okay, so we'll look into these representation in a GPU in upcoming slides. But for now, just remember we have threads. 32 threads, we have a verb, and 1 or 2 dimensional verb, we have a block, and 1 or 2 or 3 dimensional blocks consist of grids. Okay, so um, so this is like the execution process for our GPU program. So if you guys can remember, we have something called a kernel. Okay, kernel is the highest most one that you will see, the kernel function, the global function, which is running on the host. So this is like the starting point for our application. So kernel is executed by grid. So one single kernel, one single instruction is executed on grids. So one single grid can be executed on blocks. Okay, so the blocks are executed by warps, and the warps are executed by threads. So the smallest point of execution of a kernel function is going to be a thread. Okay, so let's know these function in here. Just to give you an example, the when we are starting a program, the kernel is where we when we start something, the kernel knows okay, how many grids, how many blocks, and how many verbs, and how many threads are there. So basically, when we execute a kernel function, the kernel function knows what are the blocks and what are the threads that is available, and based on that, we assign the task. We give each of the application to execute the instruction. Okay, it will make more sense when we look into the diagrams of the program execution. That's for now. Remember, these things are hierarchical in this manner. Okay, let's take a closer look on the program execution, so we know what's happening in this space. Okay, so the first thing we need to know that the host code. Okay, host code is what we call that execute in the CPU level. And in host code, most of the time, the sequential stuff, the preparation for the application, and the execution on the pre-execution of the parallel computing stuff happen on the host code. So whenever we want to execute whenever we want to start executing the program, when we are looking into the application starting point, the host code is where we start our code, and all the sequential stuff are happening on the host code. So nothing related to parallel or anything that happens in here. And the next thing is prepare the kernel launch. That means we need to give instructions. We need to give instruction for the device code that need to be run on. Okay, the parallel data launch happens in the kernel launch. So the host code is doing sequential stuff, creating all the necessary data, and the launch of kernel function, that is, okay, we are gonna, it's like something like this. We have this data set. Okay, we need to create that data set, and when we want to execute the data set, what we will do is we will prepare all the data that we need to go, and we will send it to the device. So that's kind of mindset is there in the host code. So everything before that, you need to execute the parallel computing of CUDA execution that happens in host code. And the next thing that we need to do is we need to allocate the memory. Okay, so whenever some languages like Java and some modern languages, the memory allocations happens automatically for us. But in this scenario, when we are executing programs, that is not the case. We need to make sure that memory allocation for these devices happens on the host code itself. So, for example, when we want to execute some host codes, when we want to execute some device code, the first thing that we need to do is prepare the data set. Okay, we need to prepare our, okay, there are like 1,000 data points. We will prepare that. The next thing is we need to allocate memory on the device for that 1,000 data points. Okay, so the GPU, unless the GPU is occupied with something else, we can allocate memory on the device. Let's say for the 1,000 data points, we need X amount of memory. So we will call the device. We will call the device and we will say, hey, I need X amount of memory in your device, and please allocate that for me, and I will copy the data from my device to you to start executing. Okay. So first thing, the next thing is that you're going to do is allocate the memory on device, so others won't be taking that space while we are executing the program. And the next thing is the copying data from host to device. That means we have prepared our data set. We have prepared everything that we need to execute on device. We have allocated the memory. And the next thing is we copy the prepared data from host to the device. So the device, the host knows, okay, now the data preparation is done, the memory allocation is done. Now I'll copy all these data from my host to the device. So device copying happens. Once the copying is happened, so everything that we need to start execution, the parallel program is ready. So what we'll do is we will launch the kernel. That means you guys can remember the kernel function is like the starting point of our application. We launch the kernel function, and the GPU, what it does is, okay, now I have all the data, I have allocated the memory. I'll start executing. The kernel function gives the signal. Okay, we can start executing the instruction given to the GPU. So the kernel function starts. Kernel function will start executing all the things that they have received, especially the data and the functions that we have written. All the things are done. Once the execution is completed, once we know the parallelization is completed, the device have the results. Okay, device has the result. Okay, this is the end result of running this GPU function. And what we need to do is we need to copy back the data from device to host, saying, okay, device has been executed completely, and we will be copying these things back. Okay. And one key step is missing in here, that is clearing the memory. Once you are done, make sure to clear that memory, clear the space. Otherwise, the memory will be hogged, or someone else can't someone else might not be able to use that. Okay, the free memory should also happen. Okay, so this is like the flow of the application execution, and we will see these in action when we are exploring the source code. And the next thing that we need to know, how a GPU is executing this application, how data is copied, how to prepare the data, the preparing data, the preparing kernel launch and sequential stuff, and preparing data, and this is one of the most important thing. So unless we know how to program the kernel, unless we know how to execute these each and every section of our application, we are not doing some good works. So we need to know how threads are working, how a block is working, and how to feed this execution point with data. So normally when we are working with CPU level programming, we do not we do not have to worry about giving the instruction, giving the application data allocation and execution and all. But in a GPU, we have specific access. Since the context switching is not happening, the device itself, we are in control of doing the context switching. Okay, so we need to make sure the correct instructions are given to the thread. Okay, so in a CPU, we don't have to worry about any of these things, because the CPU does the context switching for us. When we give the instruction are divided, and the CPU is doing this context switching, and they achieve the parallelism by doing by the CPU algorithms. But in a GPU, it's not the case. We need to make sure, and we need to program what data goes in which thread, and how we execute those threads. It's up to the programmer to decide how we access these data, how we allocate these data, how we proceed with this, with these memory allocations, and everything is done by the programmer. Okay, so in order to do that, we need to know several things in this application. So the first thing is we need to know the thread. Okay, this is most smallest execution point. Thread, what is the thread, and which data that's gonna go in that thread. What is the block, and what data is execution on that block. So we need to know about these things in order to make sure that the correct data is accessed, correct data is executed in this application. Okay, so we have these simple diagram which we will use to identify what are the threads, what are the what are the threads, how we execute these things. So in order to have a mental picture of how the threads and how data is programmed into the GPU. So we will look into these right now. Okay, the first thing is we need to know that we have something called thread ID X. Okay, the thread ID X is what we call the thread ID on X dimension. Okay, remember we are talking in multiple dimensions. We have several dimensions, but for simplicity, we will be looking at only the X dimensions. Okay, that means only one direction of the dimension is we will be looking at. So IDX, thread IDX in this section is 0. The ID for this thread on X dimension is 0. And the next thread that we have, the next execution point, it has the thread ID on X dimension with 1. Same goes to here, X dimension, thread IDX is 2 and 3. And remember, this is what we call a block. Okay, we have a block. So if you want something like a warp, okay, remember a warp is consisting of 32 threads. Okay, now we have a block that executed on this section. So when we get out of these four threads, what we will have is a block of 0. And same goes to the next block. We have another block within the X dimension of 1, and it is consisting 0, 1, 2, and 3. So the thread ID and the block ID is creating what we call a matrix. Okay, so the matrix is what we use to access these individual threads. Okay, so this is a special case, special in the sense when we are allocating our kernel, when we are declaring our kernel, we need to specify how many blocks or how many threads that we are going to using, um, how many threads are for each kernel is used. So that is used, that is declared by this kernel function, and in here we are saying, okay, we have this amount of kernels, this amount of threads per that. So we have this amount of threads and this amount of blocks within this kernel function. Okay, so before we explore this thread and dimension allocation, we will revisit our kernel function. Where is that? Okay, there is the kernel function, and in here we need to make sure the kernel function is having something called the block dimension, block ID, and thread ID. So these are built-in variables that is available within the kernel function. So each and every kernel function knows what is the block dimension of X and what is the block ID of the X and the thread ID of the X dimension. Okay, so make sure we know these variables and built-in variables, so we can access our thread as we go along. Okay, otherwise this won't work. This we will accessing the wrong thread or wrong position that when we are working with the application. So one other thing launched by the host called the add kernel function is defining the grid size and the block size. Okay, so we need to make sure when we are working with the application, we are defining the grid size and the block size for our application. So when we look at our example code in here, the kernel function, we are defining a 3x4 kernel at our launch. Okay, so keep that in mind, and we will look into this application. Okay, application execution. So we have a variable called I, and the I is calculated, the individual data point is calculated by using the thread ID X and the block ID X multiplied by blocks dimension X. Okay, so by using these calculation, we can access each and every thread, each and every individual thread in our application. So if you guys can remember, we get these variables out of the kernel function. The kernel function is having these built-in variables. These variables represent the dimensions of our defined kernel levels. So by using these things, we can calculate the instruction and the individual thread that we want to execute. Okay, so let's take this example, and we will go one by one how we can define the execution of this kernel function. So remember the kernel, we have defined the size in here. So it's going to be a 3. That means it's going to have 3 dimension and 4 kernels in here. So the dimensions that we are looking at, the first one, if you want to individually find this thread in our application, so the thread ID X is 0. Yes, we have found that. And the block IDX in this scenario is 0, right? That is correct. And the dimension of the block, how many blocks are in here? That is 4 dimension, like there are 4 blocks, sorry, 4 threads in here. And multiply those things in here and you will get a unique ID for I, that is 0. So the I in this scenario is 0 and it is indicating this thread. Okay. The next thing is we need to identify this one. Okay. So how are we going to do that? The thread IDX in this scenario, thread IDX is 1. And we add the block IDX. The block IDX in this scenario is 0. Okay. In this scenario is 0. And the block dimension, how many threads are in here? You can see there are 4 threads. Okay, so the 4 threads will represent what is the dimension of this block. And in the x direction or the x dimension, we have 4. So it's executed by 4. That is going to be 0 multiplied by 4 is 0, and we add 1 for that, and we got ours a unique ID for this thread. Okay, so we have access to that. So same goes for the 2 and 3, same theory. The block ID is 0 and dimension for that is 4. So that's going to execute. That's going to end up zeros. And since these one is 0, 1, 0, 1, 2, and 3, 0, 1, 2, 3, and 3, 1, 2, and 3, we get from 0 to 3 unique identifiers. Okay. And we will jump into the next block. Okay. So you guys can see the dimension has not changed. The block X dimension, block dimension, it's only consisting 4. Around here, there is only 4 dimensions. So we have 4 dimensions, but now the block IDX is, the block ID is in here is 1. Okay, so 1. And 1 is multiplied by 4. It's always going to return 4 for this section. And you guys can see the thread IDX in here with the block ID 1, 0, 1, 2, and 3. And when we add those things with the values that we are having in here, we get unique numbers like 4, 5, and 6, 7. Okay. So this is, as I mentioned, this is the most simplest form of execution. This is only thinking only in one direction. Okay, one dimension as well. So we have this in x dimension, only in x dimension. We will have the same for other dimensions as well. So we can represent more real world data sets. Okay, in real world, most of the time the data is not linear like this, x1, x, and y. More complex ones will consist more than 3 dimensions. Okay, so we can have allocation or representation of 3-dimensional data in a 2-dimensional way, like when we are using this kind of structure. Okay, once again, remember, so this is the thread ID, this is the block ID, and dimension for this is 4. You guys can see there are four threads in here. So dimension for this block is 4. So block dim x is 4. Block IDX is 0 for this one, 1 for this, and thread IDX is by individual by these individual threads. And each of these blocks will have the same block dimension. The dimension of blocks is not going to be changing because we define that in our kernel function. We define the kernel function, how many blocks are going to be there, what is the dimension for this block. Okay, so by defining that, we are limiting our things, so we do not change anything within our application. Okay, all right. So let's make it more clearer. In here, we will take this example. Please, this is like the most important equation or most important thing that you need to remember. In here, we take the example kernel launch. Okay, the kernel has 3 by 4, and we execute this kernel function like this. Okay, we have a kernel function. How do we know it is a kernel function? The function is we have the syntax of underscore underscore global underscore underscore, and it is going to be a void one because the kernel functions are always void. And the function name in here, it is said kernel, but you don't have to name it as kernel because these two syntax will make sure that is a kernel function. And this is the input for our kernel function. These are the data that we are interested in. Okay, so you guys can remember, we can calculate the I, we can calculate the individual unique ID for this kernel. Okay, this kernel has this unique identification, which we calculated something like this. So the calculation is pretty much simple. We have the thread ID X on X dimension, block ID X on X dimension, block dimension on X. Okay, so what we do is we take the block ID X and block dim X, block dimension, and the block ID, we multiply it, and we take the thread ID X and we do the addition for that, and we get a unique number for our thread. So within our application, when we want to have a value filled out for this A. Okay, this is an array. You guys can see this is a one-dimensional array because we are using only the X dimension. Okay, we are not using even another dimension in here. We are using a single one-dimensional array. So for the ith position of the array, within the array, we will be using some value. Okay, so the I is going to be continuing, and the I is going to be continuing from 0, 1, 2, 3, or whatever the number. And the value that we're going to be putting in here is going to be the value that we are interested in. Okay, so in this particular scenario, the ith iteration will have block dimension X. So if you guys can see the output of this application, will be A represented by these numbers. So you guys can see in this example, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Am I correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 4, yes, 11 output in this scenario. Let me guess. 0 to 3, 0 to 3, 0 to 3. So there is 1 4 missing in here. That's a mistake. But for now, we will yes, 1 4 is missing. The output in this scenario is gonna be all of these things will have the array with position I will have the number of block dimension x. Okay, what is the block dimension of x? In this scenario, we will see all of these things are having the value 4. Okay, so the block dimension that we have defined, and we have assigned the block dimension for all the values in the array, and it will contain 4. Okay, why? We have defined in our kernel, when we are launching our kernel, we have said we need a block consisting of 4 blocks. Okay, so dimension for each block is going to be 4, and we need 3 of these. Okay, so we define within the kernel function, we are saying that we need 3 blocks. Okay, you guys can see 3 in here. We need 3 blocks, and each of these blocks will have 4 threads. Okay, that is the kernel function definition that we see in here. So we need 3 blocks, and each of these blocks will consist of 4. That means the dimensions, how many execution points, what is the dimension of this block is gonna be 4. Okay, so it's gonna be always gonna be flow 4 in this scenario. So we have 1, 2, 3, 4. It is something similar to this. And how many blocks we need? We need 3. We need 3 blocks. So if you add another block to this above example, it is going to be the perfect example. But if we make this 2 by in here, the number of blocks that we need, if we make this 2, it is going to be identical for this illustration that we have on top. So now we have a block dimension of 4. That means each and every block will have 4 dimensions, and we need 3 of those blocks. Okay, so we need 3 of these blocks. So the block dimension x in here is always going to be 4, and we have 12 data points. How do we know that we have 12 data points? So each and every block will have 4. We have 4 by 3. That means we have 12 data points. Okay, so the 12 data points will have, all the 12 data points will have the x block dimension x value, which is 4. Okay, so we have the array filled with, from the 0th element will be 4, first one 4, second one 4, list goes on, because we are always assigning the block dimension x. Okay, and next in the next kernel example, we are assigning the number thread idx. Okay, so the thread idx, what we are doing in here, we are assigning the thread number. Okay, so if you guys can remember, whenever we are going with thread, we have 0, 1, 2, 3, and in the next block we also have 0, 1, 2, 3. Okay, so that's why it is repeating the sequence 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3. Okay, so this will have 4 this will have from 0 to 3, 0 to 3, 0 to 3. That is 3 times. That's because we have 3 blocks. Okay, we have 3 blocks. So each and every block will start with 0 to 3. The next block will also start from 0 to 3. The next block also start from 0 to 3. So that's why we are having this block dimension of 0 to 3, 0 to 3, and 0 to 3. So that's why always the thread idx in this scenario is gonna be repeating on each other. Okay. In the next example, Okay, these are like 4 different kernel definitions. In the next example, what we have is block IDX. Rather than rely on thread IDX, we are assigning the ith iteration with the block IDX number that we got. So you guys can see there are 3 blocks. Okay, we have 3 blocks, and each block has 4 the dimension of block is 4, but we have 3 blocks. So what we need to do is we have 3 blocks, but remember, always we are counting arrays from 0. That's why we have 4 zeros. That means the block IDX for the first one is always going to be block IDX for this one is going to be always 0. Next one is always 1. Next one is always going to be 2. So that's why we are getting the 1s and 2s in here. Okay, so if you look at the kernel execution in here, you guys can see that it's gonna be the right now we are having the values from x dimension, x and block. So we have x, sorry, thread IDX, block IDX, and block dimension. So it's gonna be something like sequential here 0, 1, 2, 3, and up to 7. So this one has extra one. It's not going to be 12. It's going to be end up in 11 because we are starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. 12 is extra. This is wrong. So we will have the thread IDX, block IDX, and every time we are assigning that array in single dimension, we will have the value of the I. So it's going to be something like this. Okay, so this is how basically the kernel functions knows how we can access these values, and we can assign these values. So we are not going to be assigning the block dimension x or thread ID x or whatsoever. For demonstration purpose, what if we do the array initialization like this? This is going to be the kernel functions output. So this is what we're going to be feeding to our system, feeding for our device actually. So in order to make sure that these values are understood by you, what we do is we assign these block dimension x, thread IDX, and block IDX into our array and see the output. So we know, okay, when we are launching a kernel, the kernel has these numbers and they are working. Okay, so make sure you know, okay, the first one defines how many blocks, the second one defines what is the dimension. Okay, this is what we call the block. How many blocks? This is within one single block, how many threads are going to be there. Okay, it's 4, this is 3, and by looking at this, you guys can fill out the kernel function, right? So anyone having any troubles understanding this, because this is very important moving forward. Okay, all right, hope you guys understand. We will do some exercises on these variables. Just make sure when you are asked to write something like this, a kernel function like this, make sure to write the thread IDX, block IDX, and block DMX, and do the calculation first, then think about the value or output that we are gonna get in here. Okay, so it's gonna be easy once you understand. It's not that much of a hard when you know what these numbers represent within the kernel itself. Okay, next thing what we'll do is we will do the most simplest form of CUDA code. Okay, so unfortunately my machine with CUDA is not running as expected. So I'll just walk through the application and we will look into this. I think I should be able to get my machine up and running. We will execute this code once it is done. For now, let's look at the application and see how it goes. Okay, so it's going to be written in C syntax at least. So we will include the standard IO header, and we will use the standard libraries. So these are like something what we need to put. So if you want to print something out in the CLI or whatever you're using, we need the standard IO header. So this is like the library which help us doing the print format and stuff. So and we need to import or include the standard libraries which help us to execute the program also. And the first thing that we need to do is we need to define the kernel function. Okay, it's not like first thing, it's the easiest form. So we will define our kernel function. Okay, we will define the kernel function. So within the kernel function, we know, how do we know this is kernel? Simply by looking at the syntax. The kernel function should have underscore underscore global underscore underscore, and it should be a void. And this name, it can be anything that we like. Okay, and in this scenario, since this is a hello world application, we are not providing any inputs. That means we are not expecting any data to be populated or anything that we need to do. We'll just have this kernel function, and it will just print out our inputs. That's it. So we are not populating any data. We are not doing any data allocations in here. We are not assigning anything. We just want to see whether this code is getting executed. And within the kernel function, you guys can see we have a print statement. Okay, print f, and it's going to say simply hello world from thread, and these placeholders, and from device. Okay, so we will be executing this string. Okay, just this string. It's going to just say from the thread, this placeholder will have the first value, the second placeholder will have another value. So the first value that we will see in here is the thread IDX. This will have the thread IDX, and the next one will have the block IDX, the block identification. So as you guys can remember, these block IDX and the thread IDX and the block IDX is variables available within the kernel function. You don't have to define it anywhere. These are accessible. These variables are accessible within the global function. So even though they are not defined in anywhere, these are available within the kernel function. So within the kernel function, you guys can see that the thread IDX is here, and the thread IDX in this scenario is will be placeholder for this one. The block IDX in this scenario will be placeholder for this one. And the most simplest form of kernel function, we are not doing any allocations or anything. We are just printing out the thread IDX and block IDX. So this is the kernel function. As you guys can remember, the kernel function is going to be executed in device. Okay, this is not going to be executed in the host, which means this is a GPU function, or this will be executed in our device, the GPU. And so that we can assume that from device is making more sense. Okay. And the next thing, we will have to look into the main function of the application. So it's going to be the simplest form of C++ code. And in here, you guys can see the the main function will have the will return an integer. This is like this system code, what we call whether it is executed completely or it is not executed. So the main function will also not take any inputs from the command line arguments or wherever we are wherever we are executing this. So it's gonna just print hello world from host as a beginning. So whenever we are executing, this this code will start to execute hello world from host. Then we are invoking our kernel function. You guys can see we are invoking our kernel function. When we are invoking our kernel functions, you guys can see we are not giving any parameters. We are not going to be passing any parameters because it is going to be a void function. We are not giving any inputs for the kernel function. But one thing we need to do is we need to make sure we define the what we call the blocks size, and the next parameter is that we're going to be using in here the size of the blocks. Okay, so this is the dimension. Okay, within this block, within this kernel function, we will have a block dimension of 1, and we will have one single block. Okay, so it is going to be the most simplest one that we will see. It's going to be one single thread in here, because only one dimension, that means in here it's going to be 1. That means we will have only one thread, and the dimension for that, the how many numbers of blocks that we're going to need, we will need only one. That means there won't be anything from here, there won't be any other than this block. So it's going to be one single thread within the kernel function. So we know only one dimension and only one execution. So in here we will see 0 and 0, because as you guys can remember, even though we define the numbers in integers, the array, the IDX will start from 0. In here you guys can see the first one is 0, the block dimension also going to be 0. Okay, block IDX and block dimension, it's going to be 0. So it's going to say hello world from thread 00 from device. Okay, so we have defined the kernel function. Kernel function is called within the host itself. Okay, the kernel function initiation part that we need to do is happening within the host code itself. Okay, so we can only call the kernel function in here. Say for instance, we have any device functions. If we have a device function, those device functions should not be called within the host, because the device function only can be called within the global function or another device function. Say for example, this is the GPU code that we are running, and this GPU code, we can't put everything in here. It will make the kernel function a little bit hard to read, hard to understand. So in order to make sure that we are breaking down the kernel function, we can have device function. If you guys can remember, we had the concept of device function in here. So the device function is understandable by the key by the syntax __ device __, and it cannot be called from host. That is the main function, but it can be called from kernel or other device function. So you guys can see the device function is only accessible or started from the kernel function, then move on. And also remember, kernel function can return a value, but not the device function can return a value, not the kernel function. So we can easily identify a device function and a kernel function. Okay, So the next thing is CUDA device synchronize. This is where we execute the code, as you guys can remember. We are not doing any memory allocations in here, but we need to make sure we say, hey CUDA, now our kernel function is ready, just execute and do the necessary. Okay. And since this application it is a simple one, we are returning 0. That means indication of we have successfully executed this application. Okay. So if this one had some errors, the device was not ready, something like that, or the thread was not accessible, the device is not functioning, then what we need to return something else, something like an error code. But for simplicity and for easiness, we'll just return 0. That's indicating a successful execution. Okay. So the most important thing in here, this function call, okay, please remember the dimension. This is the dimension of the block, and this is the number of blocks. Okay, that is the most important thing that you need to remember. So we will have one block containing one dimension. Okay, so based on this, you guys should be able to fill out this in a case. If you have something like this, you should be able to fill out this and fill out this one as well. Okay, so this particular example, the kernel function has 2 by 4. That means the kernel is in here 2 and 4 for this scenario. In this scenario, we have 3 by 4, and the output will be there. Any number of kernels and dimension, you guys should be able to give the examples, give the output at any dimensions. Okay, we are not going to make it much more harder, but at least some sort of clarity should be there how we need to calculate this within our kernel function. Okay, so we have seen the simplest form. Just digest as of it is, and we will see more examples as we go along. Okay, so this is the simplest form. We only have dimension x. Okay, we are not even thinking about more than 2 dimensions. It's going to be a little bit hard to understand without without hands-on experience on CUDA, and we need to play around it a little bit more to understand more than 3 dimensions. It's for us, for humans, if you do not have a good understanding or good practice on um, um, good understanding of dimensions, it's us as humans, it is a little bit complicated to understand more than 3 dimensions, because we are living in a world of 3 dimensions. Thinking about a dimension other than that, it's going to take a little bit of what do you call special thinking. Okay, we should be able to have that kind of thinking pattern. But first, let's try with the most simple, the x dimension or a single dimension, and we will work on that. All right. The next thing that we need to look at, we probably have seen the CPU architecture. We will use the GPU architecture, so we know what's really happening in here. Okay, so when we are talking about the GPU architecture, we talk in 2 different views. One is the hardware view, and the other one is the software view. Okay, so if we tear down a GPU, you will see what you see in the left. But when we are talking in our application, when we are talking in software terms, we will probably see this kind of view. Okay, so let's talk about the let's talk about the hardware specification, how hardware is really doing these things, and it will be something similar. Okay, only the words that we are using is gonna be what we call differentiation in this manner. Okay, otherwise they have like a one-to-one mapping, but when we are talking in hardware view, we have different terms. When we are talking about software view, we have different terms. Okay, so if you take the hardware view in here, okay, so we have the GPU device. So this is what a physically what we will get. We will have a GPU device. Okay, within this GPU device, what we will have is the GPU memory. Okay, so whenever we are copying from host to the when we are copying some instructions, some values, we will be interacting with this GPU memory. Okay, it's going to be something like RAM that we use within our application. So something similar, we have this GPU memory within our application, within our hardware. Okay, and then we have multiprocessor memory, what we call a specific memory type that is available for this stream multiprocessor. Okay, so we will have the hardware terms stream multiprocessor. Okay, but in software we have something similar, but do not get confused these terms in terms of software and hardware. But stream multiprocessor, this is where the application this stream multiprocessor, the SM that we talked about, its own memory is going to be here. Okay, so we have two type of memories in here, the GPU memory and multiprocessor, stream multiprocessor memory, SM memory. So each of these sections are having their own memory, and we have something for the whole GPU as a memory. Okay, so these two things do not get confused. So we have something for the whole GPU device, and we have some memory for stream multiprocessor of each of these sections. Okay, so we have the multiprocessor, that is the stream multiprocessor. This is where the execution happens, and we have a SIMD course. That means multiple single instruction, multiple data course. Okay, so if we talk in terms of hardware, this is what we will see. Single instruction, multiple data core is there, and we have the multiprocessor. The multiprocessor has its own memory, and the GPU has its own memory, and the whole thing makes up a GPU. Okay, this is like the basic hardware version of our GPU. And then again, if we talk about the software view, which we have been talking so far, we talked about everything that you see in here, the kernel, blocks, and threads. So those are the terms that we use in the software view. Okay, the software view that we are talking in here is what we have so far talked about. So the kernel here represent the GPU device. As you guys can see, the kernel is where all the magic happens. The GPU has one single kernel. The kernel execution happen within this GPU section. So the GPU device is going to be one single big kernel. So the kernel in here, we have something like this. And each and every kernel have a device memory. Okay, we call this as a global memory as well. So we have this device memory which everyone can access. Okay, then we have these blocks. Okay, which we talked in detail. So we have blocks in here, and block have specific memory. That is what we call the block specific memory or a block memory. And within a block, we will find threads, and these threads are the execution point for our application. Okay, so you guys can see it is like one-to-one mapping between the hardware and software view. But when we are talking in hardware, we do not call that the kernel as GPU device, because in hardware it make no sense to call it is the GPU device, but in software it is like the whole kernel execution. Okay, so we have SMID cores, but in software terms we call those string threads. Multiprocessor as blocks. Multiprocessor memory, we call this block specific memory. GPU memory to device memory. So we have the same architecture, little bit of difference between these little bit of difference in terms of in software. Okay, so we have most of the time as programmers or the application developers on a GPU, we'll be looking at the software view. But if you are someone who's trying to understand the hardware or trying to develop in let's say in future, you need to understand the hardware view as well. Okay, this is the hardware view and this is the software view for our application. Okay, so we have the CUDA threads. In hardware, we call CUDA core or SMIMD cores. We have CUDA blocks, and we call in hardware level the multi-stream processors, streaming multiprocessors, sorry. And we have the grid or a kernel, the whole execution point. We have the whole GPU device. So it's one-to-one mapping in here. Okay, so we will talk each and every each and everything with this concept as well, because we know that okay, there is something called thread, there is something called blocks and everything, and we know in hardware level these are the SMID cores. In software we call these threads, but we will talk a little bit more about these terminologies, because it is important to know what and how each and every one of these is corresponding to something. Okay, so the first thing is we know all we talked in lot about threads. These are like the execution points, but we'll try to add more details to this in this. So CUDA thread executes on a CUDA core. Yeah, that is true. CUDA core, CUDA thread is execution on SMID core. That is true. CUDA threads are different from CPU threads. That we also discussed. CUDA threads extremely lightweight and provide fast context switching. Okay, so CUDA threads are extremely and provide fast context switching. So that means if you guys can remember, CPU context switching happens once the instruction is executed, but CUDA, it is sticking into context switching up until the execution is fully executed. Okay, the reason for fast context switching is due to availability of large registry on the CPU and hardware-based scheduler. Okay, so whenever we are doing a context switch, okay, whenever the CUDA is done with execution on a specific algorithm or a specific kernel, it need to change. I mean, it's not like thread is gonna execute. A thread is not gonna execute each and every day the same instruction. It need to change at some point, but the change is only happening on execution end, and when it is it is doing the context switching, the context switching is much more faster, because it has two characteristics: a large size of GPU and hardware-based scheduler. So the hardware-based scheduler, the scheduling happens when we are, as I mentioned earlier, when we are done executing. Okay, the hardware level. Okay, we say this execution is completed. Now you can reuse this. So based on that's logic, the hardware level scheduler will change the context. That means will replace the logic that is executing in the thread with something else. In a CPU level, this is not happening that much fast because of the software or the context switching is not that efficient, because we do not have we have hardware based scheduler, but that scheduler is changing rapidly comparing during the execution time. The execution time when we are executing so many instruction in CPU, the context switching happens, but in a CPU level, the context switching takes a little bit of time because it is changing. It is changing in mid execution. Sometimes the execution is not completed. Sometimes we need to transfer those data to something else. So that's kind of it's like we are not completely done with the execution, so we need to preserve some context and everything. So it takes time to do the context switching. But in GPU is always going to be changing the context after the execution is fully completed. The hardware scheduler has nothing to transfer, nothing to worry about. We just switch it and we fill it in. Okay, so there is no handover, there is no waiting. We don't know to persist the context and everything. We'll just switch. That is. So that's why the CUDA threads are more faster than CPU threads. The execution happens way so faster. And the next thing is large size of GPUs. That means large register size of this GPU. That means we have so many threads. Okay, so we have so many threads that we can execute. That we can execute instructions. Okay, in a CPU, you don't find that much of threads in an application. You have very limited amount of values. So you don't have so much options in CPU in terms of exchange in the context. But in here, you guys will get a lot of threads, so we can easily allocate something for our threads. If it is not available, we can check. We can take another one. So the availability of threads will help in a huge way. So we need to make sure the context switching in CUDA threads happens because the execution complete. Once the execution is completely done, once the execution is completely done, we are switching the context. And if you want to do that, there are large size of registries. That means large size of thread is available to do so. So given these circumstances, the CUDA threads are more efficient when we are doing the context switching. Okay, but it doesn't mean it is the best one, because as I mentioned earlier, CPU and GPU are doing two different things. I mean, obviously both of them are doing computing, but in terms of computing, the CUDA threads do a different job. Okay, it's good for short term of executing the stuff, and long term awaiting IO based ones, the CPU is doing a good job. Okay, the thread context is present in registry compared to the CPU, where threads reside in a lower memory hierarchy, such as cache. Hence, once the thread is idle or waiting, another thread is ready, can execute almost with no delay. Each CUDA thread must execute the same kernel and work independently of different data, SMMT. So The other reason is that the the application execution is so fast. You guys can remember when we are executing these kind of threads, when we are executing everything, each and every thread will execute the same instruction. They will be executing the same instruction. That's why SI is standing for single instruction. And these instructions that we are executing is gonna be, the instructions gonna be the same for everything. The data is what we are changing in here. So compared to thread switching that is happening in CPU, the CPU has limited amount of threads, and the instructions, all the data that we are going is going to be something handled in lower hierarchy as the cache, the L1 cache or L2 cache. That's where the device memory is going to be for CPUs. I'm talking about CPUs. But in terms of GPU, you guys can remember in here, we have block specific memory. Okay, so the block specific memory can have or will have the data for these threads or data for this whole block in instant access. Okay, so whenever a thread need data, it is right there. It is right there within the specific block. But if you want something something that is within the CPU, when you need to have that kind of information within the CPU, the problem is the memory access, it is not within the CPU. The registry is not that huge. If you want something something to be accessed, we need to go lower level or huge. We need to go a level little bit down to fetch that data. Of course, we have registries within the core, but registries are, if you guys can remember, these are really small memory type compared to other type of memories. So we, if I recall, the CPU have registries, then we have L1, L2 cache, then we have RAM. Okay, that's how the CPU works. So any large amount of data, if you want to execute a large amount of instruction, what we need to do, we can't put everything in registry. We need to put those things in L1 cache. And once the execution is done, we need to retrieve the next part or the upcoming part for the execution to happen. So the CPU is taking a little bit of time to retrieve data from L1 cache to execute and everything. But in CUDA, it's the other way around. We have the same instruction, but multiple data, and the data is rightly available within the block itself. Okay, so we have less context switching. We do not want to copy here and there. The data is available within this block specifically, and once the block is done executing, we have the data right around to we have the next set of data right around there. Okay, so the data is changing, the instruction is going to be the same. So instruction is going to be same, the data is changing. But in CPU, that is not the case. We have different instruction, different data. So that is making a little bit hard to do the context switching. But in CUDA, we have the same instruction executed each and every time by block. Only the data is going to be different. So we have less of context switching happens in the world. So if we take this kind of example in real world, let's take an example and you guys decide which one is more effective compared to other. So for example, we have an assembly line. Okay, we have an assembly line. So in the assembly line, what we are assembling is, let's say we are assembling a simple, let's say we are assembling a new phone. Okay, so the assembly line contains like this. First, you have the motherboard, and the next one is you insert the screen, and the next last step is inserting the back cover. Okay, so it's like the simplest form of assembly line: motherboard, back and front and back. Okay, so like three things that we need to do to assemble one thing. So we have two way of execution this thing. Okay, two way of execution. The first one is a single worker will take the motherboard, flip it again, have the the front installed, and flip it again, have the back installed, and screw things up and move along. Okay, a single person doing all this stuff. And the next thing that we can do is we can have an assembly line where first person job is to put in the motherboard. That's it. Okay, then there is nothing else. The second person job is to put the front and flip it. The third person job is just to put in the back, and the fourth person's job is just to screw things up. Okay, screw everything up and tight, so the phone is assembled. So in assembly lines, if the single person is doing such a thing, there can be complexities. So first thing she or he need to do is get the motherboard in, take the front in, and flip it around, get this back cover in. So they have different parts. Okay, the motherboard is one part, the front is one part, the back is one part, and screws are in another place. So when they are doing this kind of work, they have to context switch every time. They take the motherboard, then take a different turn and take the front, and take the back and have it along, and take the screw and the screwdriver and screw the everything's up. So if the single person is doing that, they need to context switch every time. They need to take a different equipment at the same time. They need to take a different part at every time, and they will be waiting on some things if something goes wrong as well. Okay, so single point of execution, we need to do context switching much more even, and it will uh, 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 it will have so many instructions to execute at a given point. So luckily, the CPUs or computers do not, once they are programmed, they are executing everything in order. But as humans, they can make mistakes. Okay, but let's keep aside the mistake part, and we think this is a robot doing or a super trained one is doing. So while we are doing the context switching, there are no errors. Like for instance, when we put the motherboard, the next thing should be putting the front, but accidentally someone put the back cover. So that can happen for human, but if you are trained enough, if you are good enough, you don't that mistake. You do not make that mistake. But let's assume that the context switching has no mistakes like the computer do. So the overall work for a single person, they have to put down the tools, they need to take the screws again and everything. It will take a little bit of time. But think of a place where a single person job is only one thing to do. Okay, the first person job is to just put the motherboard and move along. Okay, the second person's job is to put the front, move along. As you guys can see, there are no or less context switching between the tasks, because everything happens in a line. One person's job is to just put one thing, do one thing, and that's it. Okay, the rhythm is what we call very short. The rhythm is very short. One person might put anything, that's it. The second person's rhythm is just put the front, that's it. Third person's put the back, that's it. Fourth person, they don't have to do any context switching, they just have to take the device, truth, everything's up, move along. Okay, so we can see that when we do less context switching, sometimes, I'm not saying all the time, when we do less context switching, it help us to have uh, it's helped us to have less amount of tiresome in blocks compared to other things. So you guys can see sometimes the in this special scenario, the context switching is what we call is faster than the other things that a CPU does. So GPU context switching happen very rarely. Okay, so it's doing the faster execution. Okay, so different threads or multiple threads will help to do the context switching much more faster. Okay, hope that clears things out. Why threads are more faster? At least CUDA threads are more faster than the CPU threads. Okay, let's move on to think about blocks. Okay, so CUDA threads are grouped together into logical entity called blocks. Okay, so remember, these blocks represent a logical entity that is consisting of amount of threads. A CUDA block execute on single stream multiprocessor or an SM. You guys can remember a block is executing on one single stream multiprocessor, like what we have seen in here. One block runs on a single SM. That is it. All of the threads within the block can only execute one core in SM and do not execute on the cores of other SMs. So when we are executing blocks with a single SMs stream multiprocessor, that's it. There is nothing else is executing within that stream multiprocessor, because the block is always executing the same instruction. Each GPU may have one or more stream multiprocessor, and hence the efficiency make use of the whole GPU. So GPU can have more than one or more multiprocessors. So we are using that. In compute capability, you guys can remember how many SMs are available, and based on the SMs, what is the compute capability and how much executions can be done within one single one single context. Okay, so remember, in GPU, SM counts, the stream multiprocessor count will make how good or how the application, how GPU is good and how much it can take. Okay, remember, the more SMs you have, more stream multiprocessors that you have, you can execute more details. You can push more things into your block, and it will execute much more faster. Okay, so you guys can see that more of these stream multiprocessors will be providing more space to execute more things. Okay, so make sure the number of SMs, stream multiprocessors, will give you an idea how much these GPUs are giving capabilities of. Okay. All right. Let's see in our application what is like to have multiple stream processors and how it works. Okay. The next thing that we need to know is that the grid or the kernel itself. Okay, CUDA blocks are grouped together into a logical called CUDA grid. A CUDA grid then it is executed on the device. Okay, so as the name implies, all the CUDA blocks are grouped together to uh, make a kernel or a grid, so that it will create the kernel itself, the whole device as execution point. Okay, so the device itself we can consider as kernel, as you guys can see in here. The kernel itself will have all the things that we need to execute the program. All right. Okay, so there are like different architectures for these GPUs. Okay, so we will be having like, this is like the base model for any GPU, but there are different GPU architectures that's changed a little bit of the implementation of implementation of these the arrangement or the arrangement of these SMIDs and threads and all. So there are like 4 different main architectures you guys need to know. So let me give an assignment on that. Like, there are actually 5, if I can remember correctly, 5 different architectures that you guys need to research on. Let me give that as one of the things. Research about different GPU different GPU architectures by NVIDIA. Okay, so I'm vendor locking in this scenario because these GPU architectures will be different on each, but it's not like every GPU will have the same architecture. The base of any architecture will be something like this. This is going to be the basic version, the dumbed down version of anything, but it's gonna vary from different architectures. So it is more robust, or the different processor levels will have different CUDA levels and everything. So you guys do the architectural changes and see how it is changing the things in GPU space. Okay, so we are keep innovating by innovating these things. They have different architectures. So you guys know the generations, like what's we have. We had the right now we have the RTX card. So the RTX card have different stream processors. We have GTX, which was the older one, and we have special GPUs for cloud, and those applications, those different GPUs has different architectures. Okay, so you guys have a look around those things, so to get a better understanding of the more extended version of this GPU architectures. Okay, so this is going to be the base. Okay, and for anything that's going to be base, but Special architectures might be different from a little bit here and there. Okay. The next thing that we will be talking in our section is going to be the CUDA memory models. We almost touch upon here and there, but we will be looking into more specific things in here. So in memory model, in terms of the memory model, how the memory is accessed by CUDA, we will look into these different sections. So this is the mental model behind the CUDA memory model. So registers and local memory, we have shared memory, we have const, and we have global memory. So we will look into the device itself. It's more easy to understand by looking at the diagram itself. Then we will look into the definition on each. So you guys know we have the host. The host is where we do this the initial code sections, but once we copy over, or once we hand over the things to GPU is something that's handled afterwards. So in the host, we do not talk about that memory. We know that there is a CPU related one, but in the GPU, on the device or the grid, this is like the whole kernel. And within that, you will find two memory spaces. One, it is called a global memory. And we have the constant memory. So why do we need two different memory types? We have the global one, the constant one, both are within the device. So why there are two? So the arrows that is pointing directly to these applications, or to these threads, represent why it is so important. You guys can see that in global memory, you will find arrows are two-headed, but in constant memory, you will have one-headed or one-headed arrow that represent itself. So the constant memory is going to be used for unchanging values. So that means, as the name complies, const will have variables or values that is throughout the kernel. It is going to be not changing. The values that we have put in constant memory, it's not going to change throughout time. But in global memory, what we will do is we can store these values in the application, and the threads can access those things, and thread also can write to those things. So it makes the global memory available for all the blocks as well. You guys can see that all the threads are accessing the global memory, and the block in here, the block 00 and block 10 has the same access level, or they can access the global memory from block 1, and blocks 1's threads even have access to global memory. So it's going to be something like a shared memory throughout the kernel itself. So do not, the general practice is do not write applications, or do not have global memory space as a communication mechanism. We do not do that, but in a rare case, we can use that global memory to communicate between these blocks, but that is something like what we call an anti-pattern. So we do not do that. But we have this global memory where we can access from each and every thread and block. So they are sharing this throughout the kernel or the device. In contrast, the construct memory, it is something available for everyone, but it is not changing during the kernel execution. During the kernel execution, those values are going to be const. And once the execution is done, you can free it up, or we can have it differentiated or changed in kernel changes only. Okay. And the next thing that we will probably see is that registers and local memory in here. Regular variables declared within the kernel. So these things are declared within the kernel itself. The thread has that access to that, each and every one. And we have the shared memory. The shared memory is what we call within the threads. If you want to communicate between threads, okay, allow threads to communicate between these blocks within the block, okay, we have the shared memory. So the shared memory is only available within the block scope. That means a shared memory within block 0, 0 is not accessible from 1, 0. It is only available for this block only, and whenever these threads are communicating, they can use this shared memory to communicate them. So we have seen how shared memory can access the application and communicate with each other. Also, same goes to the registers and local memory. These are like registered. We consider that like the fastest memory access for this thread. Whenever we want to, if you guys can remember, the threads have the multiple data section. Okay, they are executing multiple data. So whenever we want to execute something, when we are assigning values, when we are executing the values that we got from the kernel, these are either reside on registries or local memory. Okay, based on that, they are executing the values. Okay, so memory model is something we need to be very careful. We need to understand what are the scopes, what are the restrictions, and what sort of use cases are there for each and every of these memory models. Okay, all right. The next thing we'll do is we will look into more what do you call advanced example. Okay, so we know we have seen the simplest form, the hello world, and we will go into a more advanced, more sophisticated one with CUDA execution. Okay, so this kind of code is something that what will be expected on your exams as well. So you guys need to make sure you know each and every line of these code, and you should be able to explain what's going on in this code or line of code, and how these things will affect how these things are executed, whether it is going to be host code or a device code. This kind of mental picture should be there with you guys. Okay. All right. Let's take the code and try to see what's going on in this piece of code. So you guys can see the default includes standard input output and standard libraries. And apart from that, we have IO streams, which we'll be using for streaming or taking in some data. And we will be using something called namespace, which is something similar to saying that, okay, this is going to be within this scope. Okay, the namespace is like a way of encapsulation of our code into one single namespace, one single boundary. Okay. And the next thing is these declaration of these variables. So we have integers, two integers. One is called A and other one is called B. So you guys see this star in here. That is something what we call a pointer. Pointer is like where we are saying, okay, we are allocating this memory. All right, this is like an initialization of this. So pointer is something that we need for initialization. So host data, whatever the data that we will be putting in here, that's going to be int A and int B. And the result is going to be C and C2. Okay, so we have 4 different variables, A, B, and C and C2. And you guys can see that this is the kernel function. The kernel function is a very simple one. The kernel function will have the name of vector add, okay, vector addition, short for vector addition, and it will take A, B, and C and N as the input for this kernel addition. Okay, so vector addition, it will take 4 parameters. Okay, let's see what is the use case of this. So as usual, we will calculate I, the unique thread execution index, thread identification. So we know the drill, block IDX, dim IDX, and thread IDX is summation to that. Okay, the order might be changed, but it's gonna comes as thread IDX and block IDX multiplied by dimension of that. So we do not know the dimension or how many blocks or how many threads are used unless we go to the code itself. Right now we have the identification in here. The simplest form is that for any addition that we do is we take the we have the A array, okay, this array, and we take the ith iteration, and we have the B, the second array, and we take the ith iteration and we put the result on C, this C ith iteration. Okay, so remember we are doing vector additions. Okay, vector addition is this is the simplest form of doing two vectors. The A and B is representing two vectors in this scenario. So we need to make sure these two vectors, the vector A and vector B, are represented in here. So we'll be having the integer vector definition in here. So we have A and we have B in here. So it's the simplest form. We'll just take whatever the ith iteration, bth iteration, and put it in C type, and doing a plus at this point. Okay, that is the simplest form. So we have the kernel function in here, and we will do what we called what we will have a CPU function. Okay, so we have the GPU function, a GPU code of this, and we will have the same function for CPU to do a comparison to indicate which one will be the fastest. Okay, so we need to make sure, as I mentioned previously, having a GPU is not going to solve everything. We need to make sure the benchmark will give us good results on vector addition. So we have another method called vector addition underscore h. So we will do the same calculation in host and see which one is better. Okay, that is like the expectation for this. Okay, and when we are doing when we are doing this vector addition, when we are doing this vector addition, the different form of addition is to be used. That's because because in vector addition that we do in GPU is going to be a little bit different in CPU, because you guys can remember the block IDX, dim IDX, and thread IDX. These are variables only available for GPU programming or within the kernel function itself. We do not have the block IDX, diamond IDX, and everything in CPU. So we have to do the old-fashioned way by simply looping through and getting the values in here. So the simplest form is we need to go for loop, and from integer 0, we are defining an I, and we have the nth. This is like the number of items within these arrays, and we will do I++ a simple for loop. Within that for loop, what we'll do is we will take the same logic in here. The logic remains same. We will add A1, which is the first vector, second vector, and put it in C1, the third vector. Okay, so this is going to be this same. As we go along, the number of items, the n is the number of items the array will loop through. Sorry. So in vector addition, which is done by the global function, the n is actually useless at this scenario. We do not need to know the n in here, because we have the block dimension and block IDX. We know the exact point that we are accessing. Since the dimension is going to be same, we will be using two different, we won't be using the number of elements in here. Okay, so in this host addition, we do not have that such a unique scenario, so we need that number of elements in here. Okay, so we have one function for GPU, we have one function for CPU. Okay, which we need to see which one is more effective depending on the number of elements and everything that we are putting in. Okay, so we come to our main function. The main function will take some arguments rather than the old one. Okay, so we'll see whether we can be using these things, but these are like the standard ones that we take the input arguments for our GPU functions. Okay, so first thing, we will just mark our beginning, the print of our application. So we will be having a vector that is this size. I'm not gonna try to it is 1,000, 100 and 1,000, I think, and 10. I'm not sure the number exactly, maybe 10 million or 100 million. Let's see, it is 100. If I go in here, it is going to be 1 million. So it's going to be 100 millions or 1,000 millions, whatever the number. So this amount of elements that we're going to be trying to do a vector addition. Okay, so we will have the number of bytes that we need to allocate. So you guys can see, you guys know that a number of bytes we need to allocate. It's gonna be affecting the memory allocation that we do in the GPU. So we will have the number of elements that we see in here. We are using this n amount of elements, and the size of an integer. Okay, the integer will have a size, the number of bytes that we have. We have to, we will have integers. We will have that amount of integers, and one integer is going to be, let's say one integer take only eight bytes, and one integer, if it is, for example, it is taking 8 bytes, and a number of values that we are interested in this amount, and we need that amount of bytes to be allocated within the device. So we need to calculate that one as well. And we have, the next thing is, we have two different variables, which is the block size and the block number. Okay, and what we'll do is, we will, since we have two vectors, okay, we have two vectors to calculate, and the two vectors have the same in size. If you guys know that vector addition can be done in a way, the number of length should be similar, otherwise vector addition won't work as well. So we have we have something called A, and it is going to be integer, and we have this sorry, we have this memory allocation malloc about this amount of n bytes. So whatever the number of elements and whatever the single amount of integer that it will take, and we will allocate that amount of memory in our host code. So the malloc is memory allocation. Malloc is a keyword in the host code itself. Okay, so when we are using malloc, that means we are memory allocation within our host code, not within the device code. First, we will allocate our memory within our host code. So malloc represent memory allocation in our host. So we are going to be allocating four different variables. We will be allocating A, B, C, and C2. All are in the size of number of bytes that we are interested in, and all those four will be within the host since the use of malloc. Okay, so we have this simple memory allocation done for us. And the next thing that we will do is, we will have another two variables, A underscore D, B underscore D, and C underscore D. Okay, and the next thing that we will do, we will define the block size. Okay, we will have a block size of 4,000. Okay, so we will have 4,000 threads within one single block. So you know the block dimension X, we will have 4,000 of that. And number of blocks, how many blocks that we need is going to be, as you can see, the number of elements that we are having, and divided by block size, and we know how many blocks that we will need. So that means the number of blocks will be defined by the number of elements divided by the block size. So we know we will be using 4,000 blocks, and how many blocks? So each and every block will have 4,000 threads. We will have 4,000 threads, and how many blocks that we will need? It's depending on the number of blocks that we are having and divided by the size. So we know the block number as well. Then what we'll do is what we will call DIM. We are saying dimension of the block, and the block size is going to be 1 by 1, and we will have the dimension of the grid, block number of blocks, and 1 by 1. So we know how many blocks are going to be calculated. This is not going to be something like the GPU can handle. Maybe the GPU do not have this block size. Okay, it's depending on the GPU itself. So in order to make sure that is available within the application, what we'll do is we will use this dim dimension of block, the block sizes that we have given, and one by one. And dimension 3, the dimension of the grid should be the number of blocks and one by one. Okay, so we will see what these are for in a little bit. Right now, it's just remember we are calculating the block size and the grid size. So the next thing that we will need is the we need to prepare the data sets. We need to prepare the data set. So what we will do is we define the variables in here, and what we have done is we need to make sure all these values are get populated. Okay, so we are creating a variable, we are creating a data population algorithm. Just simply what we are doing is we are iterating all over this an amount of numbers. So from 0 to 100 million, 100 million numbers, we will iterate, and the AI, the first vector will have the values of the ith iteration, and same goes to the second what do you call the second vector as well. So we are populating from 0 to 1 million, 100 million, the same number. So the first one will be 0, and same goes to the vector B, and the last one will be 100 million. So we are preparing our data set in here. So we need the data for calculation. So this is how we just create a dummy data from 0 to 100 million. So each and every vector, each and every array right now will have values from 0 to 100 million in here. Okay, so you guys can see the A and B now populated. This one is populated. Now we are trying to fill it out with C and see whether this works. Okay, so we have A and B, the data set is ready, and C and C2 are like the in output of our application. So we will see how this goes well. So we have created the block and dimension size. We'll be using this later. We have prepared our data set that is also prepared. And the next thing is that we need to do this. We use the malloc to prepare the memory on the host. Okay, so we need these data to be populated. You know, these data has been already populated, but we need to allocate memory on the device itself, because you guys can see the memory allocation in we need this memory allocation in host and the device in two different ways, because host should create the data set, and also it's gonna do the calculation in here with this function. So we need to allocate memory on the host to have the initial data set and also to do the calculation in here. As you guys can remember, allocating the data on the host is not enough. We need to make sure all that data is available on the device memory as well. So in order to do that, we use this CUDA malloc. Earlier it was malloc. Now we have CUDA malloc to indicate that we are allocating memory. We are allocating memory within CUDA or within the device itself. Okay, so we are allocating that CUDA memory in a different way. So you guys can see that malloc in amount of bytes, it is done by the calculation how much bytes it will take. But in CUDA malloc, we have to say, okay, we are defining two variables. You guys can see that we have defined variables in here, A and D. a underscore d, and a underscore d is the place that we're going to be is the variable that we're going to be doing the memory allocation. Okay, it's something similar to a equals integer this amount, but in CUDA malloc this is happening in the device itself, so we do not have access to that once we allocated that. To keep a reference on that, we are using this n underscore d that indicates okay, we will be allocating a memory amount of this. The size of the size is going to be the same because we are not changing any data types in the device itself. So the n amount of size of integer, that means we will be allocating a underscore d variable this amount of memory. Okay, it's the same syntax you guys can see in here, the same thing syntax, but since we are working with the device itself, we do not have access to there, so we need to make sure we follow this this type of memory allocation when we are using with the device code. Okay, so in here we have allocate the memory to a using this malloc command, and the type of n bytes is the same. So we can use the n byte in here, but to make sure that that we are doing the same thing in here, we will be using the n byte calculation, the same thing in here as well. So we are allocating a underscore d, b underscore d, c underscore d, 3 different memory allocations. The same we did on the host code itself. Okay, so the underscore d will have a indication that we are doing this in the what you call the device level. So we know that this is a device allocated memory. So we have CUDA malloc in 4 different locations. Okay, the next thing that we need to do is we have allocated the memory. Now we need to fill that memory. We need to copy the data that we are having in the device itself. The next thing that we will do is we are copying the data. Okay, so to do that, we are using the CUDA memcpy or CUDA memory copy command in order to do that. So we need to know the destination. Okay, our destination is a underscore d, which we have defined in here. A underscore d is the destination, and what is the source? What is the source of the things that we need to copy? So we have created our dummy data set from 0 to 100 millions. So this is our source, and you guys can see the size is going to be same. We are not doing the memory allocation. The size is going to be the same because we are using the same calculation for allocating memory. It's only the difference version of how we are doing it. So we are memory copying for the a underscore d with the value of we generated from here, the a, and the number of the size of each these things is going to be the same as the whole memory copying should be done using this amount of memory will be used. So the n is the number of elements, and each size of this integer is going to be the size of the whole one single element of this. Okay, we need this amount of memory, the memory size to be allocated. And the next parameter is one thing, one's very important, that is the direction of copying the CUDA memory. So we can see that we are copying from host to device. Okay, so this last argument should be CUDA memcopy host to device, because we are right now we are trying to get all the values from host to device. Before we do the calculation, we need to copy everything from host to device. So that's the direction of the copying. So we need to make sure that is also there. So once again, let me do the explanation for the A underscore B underscore D. That means we have a memory allocation called B underscore D, and we are copying the values what we will find in B, which we have defined in this for loop, which the variable B, the array will contain values from 0 to 100 million, and we will copy that one as well. So how many memory that we will be using? It's going to be the number of elements that we have and the size of the integer, because we are dealing with integer numbers, and we have integers, n amount of integer numbers, and one integer is going to be the size of integer. Let's assume that it is 8 bits, and 8 bits by 100 million, this amount of memory will be used. And from where to where we are copying these values? We are copying from CUDA memory. We are copying from host to device. Okay, this is the destination. This is the direction of the copying. So we have the variable, we have the source, we have what are the things that we're going to do, and what is the size, and where we're going to copy, the direction at least where we're going to copy. So we will copy from device to host. Okay. And the next thing that we will do is that we'll be that will measure these values. Okay. So clock T and clock D is going to be taking the current value of the of our application calculation. So we know, okay, this amount of time has been taken in our application to run this, and this amount of time has been taken in our application to execute in CPU. Okay, so we know CPU and GPU calculation. So we will first say we are doing the GPU vector addition, and we can say the block number and the block size. Okay, we have defined that in here. Block number is this amount of block numbers and this amount of block sizes that we will be using to do this calculation. Okay, just for scienciness. And you guys can remember when we are calling out the kernel function, we have to say vector add. Okay, this is the kernel function that we have, vector add, and the function that we be and the variables that we'll be using. So in here, you guys can see that we need to give the variables which is in the device itself. Do not get confused. A underscore D is what we will find. There will be a variable called A underscore D, and there will be a variable called B underscore D and C underscore D. N is just the number of elements that we're going to be using. This is not actually needed in this scenario, but anyhow, the A underscore D, it should represent a variable in the device. Okay, you guys can see that we have allocated CUDA malloc A and D, A underscore D, within the device. So we need to pass, okay, when you are executing this kernel function, you will find a variable within your device called A underscore D. You will find a variable called B underscore D, also C underscore D. Use those variables to do the vector calculation. Okay, so in here, what we are passing in here, the A, B, and C is the values that is available within the device itself, because we have copied that values in here, so we can execute that. Okay, remember, by we need to make sure we are accessing a value that is available in the device, not if we say A, B, and C in here, that is going to be totally wrong, because A, B, and C is available on malloc. Malloc means memory allocation done in our host code. So we can't have execute. We can't do execution in GPU where the variables are available in the host code. That is not acceptable. That is not doable. So we need to make sure we are passing the variables which is available on the device itself. Otherwise, this will fail. Okay. So what we'll do is next thing is we will execute this line. We'll execute this line. That means the kernel function will go on, and what will happen? It will use the available number of GPUs and everything. It will do the calculation, and we need to make sure we call the CUDA device synchronize. Then that way we will get the values calculated and synchronized back to us. And we will time, as we have timed the clock T and ND. That means we are taking the values that took us to calculate this function. So how much time we took to calculate whole this vector addition in the CUDA itself, and we can time that in here. So we took the starting point, and we took the end point. By calculating the difference, we can take okay, this amount of time has been taken to do this in the GPU. Okay. So the next thing that we will do is we will have the same thing, clock T, and start on H. H stand for host. Okay, starting time for host, and we will do the print F on. Okay, we are saying now we are doing this in CPU and see how it goes. And you guys can see we are using the vector underscore H command, which underscore H function. We are passing the values which is available on the host. Remember, the A, B, and C2 and N are available on host itself. Okay. C2 is the output where you get this output in here. You guys can see it is in the vector add. We will get the output in C2 in here. Okay. So C1 is used for the calculation. You guys can see it in here. C is for calculation and everything. So we get the output into C2. Okay. So vector add with H with host, A, B, and C2 and N will be used in order to do that. And if you guys can remember, vector add H. Okay, we talked about that. Next thing that we need to do, we call the CPU function. Okay, this is going to be in the host code, and we will clock it with the host as well. So we know how much time it took to start and how much time it took to end. Okay, so we can calculate the difference between time on device, time on host, time on. So only thing that we need to do is end date, or the end end on device minus start on device, and clocks per seconds. This is the value for constant value is how much clocks it is available per second. So we get the time on the device, how much time we use to execute this on the device. And we have the double on H, double time underscore H, which we use the end time of H and the start time of H, and divided by the clocks per second. Okay, so we are calculating the time which we spend on device and on the host. So by using these two values, we know, okay, this amount of time that we have been used to calculate this one in the host. Okay, and the next thing that we need to do is we need to make sure we copy back the result. Okay, we need to copy back the result in order to do the calculation. This will do the calculation. Yes, we will do the calculation, how much we have been executing. But the next thing that we need to do is we need to get the result back from the host. So sorry, back from the device back to the host. So we use the same command in here, CUDA memcopy. Okay, the destination or where we will be copying back is going to be C. This is the variable that we have defined in here. Okay, it's going to be back to the host, and the source of that is going to be C underscore D. That is, if you guys can remember, the allocation that we have done in CUDA. Okay, so from to C, from C and C underscore D. So this is the destination, this is the source, and this amount of values will be allocated for memory and the direction. Okay, so remember, this is CUDA memcopy device to host. That means we are copying back from device back to the host. So we have the C populated, whatever the values that we found in C underscore D. So if you guys can see, C underscore D is what we are providing for vector addition. So whatever the addition that we did is available on C underscore D, and we are getting back that from the host to from device to host by using this memcopy command. So we have the data copied back from the device to host, and we can print out the times and execution times that we have used for this. So number of elements, this is number of elements, time on device, time on host. So we can see which one performed much more faster. Okay. So I'll try to execute this one in a CUDA environment and get you back the results. Probably we'll see the results, and we will see some observations in here, especially when we are working with the number of elements. If you guys can remember, when we are even when we are doing the same kind of algorithm implementation on Java, the number of elements matters. That's because you guys can see the amount of work that we need to do within the CUDA allocation that we are doing. We need to allocate the memory, we need to copy it back, So these things take a little bit of time. Okay, let's take a little bit of time to do these things in total. But for calculation, if you are only thinking about the calculation time, then we can do something like this. Okay, we are not taking the time for copying for the device. We are not taking the time for copying back. If you are not interested in the total time, but we are interested in how fast it is, we can calculate only clock time for the device synchronization and everything. So if you take the measurement in here, we are only measuring the execution time, not the copying time, copying back time, memory allocation time. We do not take that into hand. We are only thinking about the execution time, how much it takes to execute. In CPU, it is the same thing, because obviously CPU do not have any other extra steps that we need to copy everything to a host, because we are already in host. So host is do not need any copying or copying back. It's just going to do the calculation. But in here, we need more information. So we need to if you are really interested in the clock timing and everything, we only have to take this amount of calculation. But in vector addition that we are doing in the code, we are working in this section. And finally, we need to make sure we are freeing up the values. That means freeing up the allocated memory. So we need to use CUDA free. Okay, CUDA free. By calling CUDA free, once everything is done, we are removing everything A underscore D, B underscore D, and C underscore D. So we are freeing up the memory. And so the next time we are executing, it will be free. And return 0, indicating that a successful in execution has been happened. Okay. So next time we will execute this in live environment, try to get the values. But if you're interested in, if you have CUDA installed right now, just run this code and take the values, play around the number of elements that we are going with. Just have it a small number, have it a big number, and see the difference, why the CUDA execution will differ on each. Okay. All right. That's about it, the CUDA installation. Hope you guys do not have any questions on this point, because it's all about theory. Okay.